Hey gang, if we need to test out the structural integrity of this pipe, we can kind of just look at it if we're down here, but let's pretend this pipe is 45 feet underground and we can't cut into it. How do we know that it is structurally sound and not going to fail us?
Well, today we are in our NDT program on the Hutchinson campus, and we're going to be looking at equipment like this, which helps us to see how structurally viable things are through 6 different ways that they test that in this program. So stick around if you want to learn how this works and a bunch of other things. All right, well, I'm standing here in Hutchinson in our NDT program with Sheldon, one of our amazing faculty members of the program. Could you tell us a little bit about yourself as well as the other faculty in the program?
Absolutely. Thanks for being here, Max. So I'm Sheldon McKinnon. I've been here for 5 years now teaching at Ridgewater. Before that, I was in the industry as an NDT technician for 10 years, and I worked in a bunch of different industries. I did a lot of manufacturing. For manufacturing, that's covers a lot. But I did a lot of aerospace parts, I did nuclear parts, I did defense parts, and a ton of structural steel. A little bit of pressure piping, a little nuclear, other things like that. And I'm followed by 3 other amazing instructors here. They all have more experience than me. So we have Mindy Krakowski. She's been here for 9 years now. And she, before that, was a tech for 15 years, okay? And then we have Walt Asmus. He's been here for 10 years teaching. But before that, he worked 21 years in the industry, doing a ton of stuff. He was a manager, he was a trainer, he worked nuclear, he worked aerospace, all over the place. And then last but not least, we got Jerry Volker. He's been teaching now the longest here for 12 years at Ridgewater. And before that, he has about 19 years of experience. He did a lot of power generation. He worked for Westinghouse, for Siemens. He went all over the country, outside the country a couple times. So we all bring a ton of experience to this program, and we all have our kind of individual flavor, bring our own expertise.
Okay, so let's start really broad, top level. NDT stands for non-destructive testing. Obviously the opposite of that would be destructive testing, which we can't always do. So could you unpack what is kind of non-destructive testing?
Sure, yeah. So non-destructive testing, it's referred to different things too. There's non-destructive inspections, non-destructive evaluation. They all come down to the same thing. We're inspecting, and we're inspecting the part in a way that we don't destroy it. We don't change the form or the function of it. Does that make sense?
Yep.
So we preserve that. And that's really important because when you think of destructive, that's what everybody gets excited for. They want to destroy things.
Yeah.
Every high school I ever visited, they're always like, tell us about the destructive portion.
Yeah.
Listen, it has a space in the industry. It's really important, destructive testing, right? The whole idea of destructive testing is you take one sample and you sacrifice it. You break it apart to measure its mechanical properties, right?
Sure. Yep.
So the tensile, the hardness, whatever you may need to measure.
Yeah.
And that's really good. You need to know that. I can't tell you that non-destructively, so we need destructive. But the problem is that one part is representing an entire batch of parts.
Sure,
right?
Yep. I have 1,000 pieces.
Exactly.
This is just one of them you're going to test.
Yep.
Yep.
So then, as you can imagine, our manufacturing is not perfect.
Yeah.
You're telling me that 999 other parts won't have some sort of imperfection that might not match that? Mm-hmm. That's not always the case, right? So destructive testing is important. We need to do it. But what we do is we bring assurance through these customers, these manufacturers, that the part that's going into service, that's going in your airplanes, in your submarines, that part has been inspected and that is good to go, right? Yeah. So I'm not a representative part at all. I do the actual part that's going into the field.
Sure.
So
you
that's
can't just
why
keep destroying airplane wings. That's
exactly.
a little harder.
Yeah, I don't think I'd want to fly in the plane that was only representatively inspected, right? Sure. Another airplane was broken down and inspected, and this one they said is fine because that one worked.
Right, yes.
That's not comfortable for me.
Yeah.
I want this part inspected.
Yeah.
So that's what we do.
So would you say NDT is a bit like quality control?
Yes,
yeah.
100%.
Okay.
We're one of the many parts of a quality control.
Yeah.
We're pretty specialized. We tend to be non-destructive testers and not do necessarily much else. Mm-hmm. Sometimes some positions we do a lot of dimensional measurements, things like that as well. But we're one of the many parts in the process that they're called reactive, right? We're not preventing necessarily an error. We're preventing something from going into the industry, but it's after something goes wrong, we find it before it gets to that point.
Okay.
Right? So the other opposition to this is quality assurance,
yeah.
right? And that's a preventative measure. That's usually good procedures, good documentation, things like that to keep things from happening. We catch it before it leaves.
Okay.
That's us.
Awesome.
Yeah.
Okay, so in what sorts of industries, you mentioned nuclear, aerospace, what sorts of industries typically use NDT?
Yeah, that's a good question. I get that a lot. Pretty much every industry you can imagine, honestly. Whenever an industry has a product that if it goes something really wrong, could hurt somebody, safety reasons, or if it's just really expensive to replace, right? Maybe it's part of a huge system that's really expensive. If something goes wrong, something else goes wrong, it's a chain reaction. These things always need inspection. You need some sort of assurance that that's not going to happen, that that weld that's put in is really good, right? That that material doesn't have any defects in it, right? So we find ourselves in every industry. The common ones that we end up seeing is nuclear power generation is huge, right? There's a ton of safety involved with that. The government's directly related with the NRC, so we have a bunch of inspections we do all the time. Any sort of defense contract, if you're talking about weapons platforms, you know, you're talking about submarines, destroyers, ships, whatever it is, all of these things need to be top of the line integrity, right? Yeah. You don't want, if a ship gets hit by a missile, you don't want that thing to sink. Right. And there are cases of that happening in the United States. In the wars, they get a huge blast, the hull is in pieces, and it can limp back to shipyard because of our integrity. And that's what we're doing. We make sure that we have the best of the welds in there, the strongest strength. So we have a ton of other industries. Power generation is huge. Manufacturing kind of encapsulates a lot of industries. Sure. But every new skyscraper that ever goes up, every one of those welded joints need to be inspected.
Okay, yep.
And if you think about how tall those are,
it's a lot of joints.
That's a lot of joints.
Yeah.
It's a lot of work out there.
Yeah. And so when you enter into this field, are you typically in a specialized position on a broader team that might be under quality assurance, quality control, or are you typically part of a specialized firm? This is what your company does and you get outsourced to, you know, skyscrapers that need to have you come in and check?
We do both.
Okay.
100%. So a lot of times a manufacturer manufactures the same part over and over, and they have such a large volume that they want to place one person full-time doing that. I would say probably the more common is a contract services, right? So you're hired by a company, and this company has contracts from a bunch of other manufacturers, right? Maybe their volume is low, that doesn't warrant one of their own people being an inspector.
Sure, yeah.
Or it's just too much. They can't possibly hire that many people internally. So they hire this contract service. So yeah, we have both in our industry.
Great. All right, well, I'm ready to get my hands on some testing stuff. You're gonna show us a few demos?
Absolutely.
All right, let's do it. So what are we looking at here?
So these guys, they're doing ultrasonic testing, right, Max? So when we talk about ultrasonic testing, we're using sound to look for things or measure things. And the way I like to imagine it is like a submarine sonar or like in a bat's echolocation. We pulse sound in a part and it travels through, it'll reflect off things and we can listen for those reflections.
Sure, yep.
Okay?
Yep.
So what these guys are doing is they did a calibration earlier. So they had some known dimensions and they listened for that response and they assigned that to a value, right? Okay. A thickness value. Now what they're doing is they're applying it to a part that has thicknesses that they don't know. And they're going to measure those thicknesses. So yeah, so all they have to do is they have to use a couplant because our ultrasound, the frequencies we use, does not like air.
Sure.
We don't do air very well.
All right.
And you probably have seen, you know, pregnancies being inspected. Yep. You always put the goop on there, the jelly, the couplant.
Yep. And
then you put the transducer. Go ahead. And he's got the screen set up so it shows out the exact reading that this is an aluminum material and that 0.19 inch, that's the thickness that they're looking at.
Okay. Do you warm the goo up ahead of time like in pregnancy?
No. We don't care about
just room temperature,
the materials feelings.
Yep.
Yeah.
That's perfect. And you just kind of move it around there.
Yep. And then you can record that reading.
Yep.
And then you can go on to the next one. Here at Ridgewater, we offer 6 what we call core methods of inspection. Okay. We have a visual inspection, literally everywhere, all the time, right? The most common inspection method, because whenever you do any other inspection, you do visual as well. Liquid penetrant testing, magnetic particle testing, eddy current testing, then we come to the big boys. Ultrasonics, volumetric inspection. And then lastly, radiography. Same thing, volumetric inspection.
Awesome. All right, so where are we now? What are we looking at?
Okay, right now we're looking at the It's kind of the advanced version of ultrasonic testing.
Okay.
This is called phased array ultrasonic, okay? So
Phase array, was that taken off of a fallen alien spacecraft, this technology we've harvested?
technically it's phased array, not phase array.
okay, yeah,
okay,
yeah.
different.
Yeah.
So it's an array that's in phase with each other.
Okay.
Okay. So what we have is I have a transducer with a whole bunch of little elements inside of it, and they're all in phase with each other. That's your array of transducers in
Sure,
phase.
yep.
So normally when we talk about conventional ultrasonics, it's one sound beam, one crystal sends a sound out.
Yeah.
This we have 64 of them,
Okay.
and we send a whole wave of sound into the part. And what we find is we can get a lot more data out of that. So what's happening right now is I'm sending a beam of sound through this part, and I have a whole bunch of holes in this block, right? And in our screen, I can display that. Each of these red dots are that hole, right? So what we had just looked at before is measuring thicknesses. Now we're entering a whole different ballgame.
Sure.
We're doing flaw detection.
Okay.
Right?
Yep.
So our holes here are representing what a flaw would look like.
Yep.
Maybe a crack, maybe porosity inside a material, maybe a non-metallic inclusion.
Sure.
Okay.
Okay.
So some sort of flaw that would give us reflection, and we can get a really good view inside of the metal, and we can scan, and we can even size how big those holes are
Yep.
using ultrasound, because this whole wave of sound gives us enough information to be able to pull that out of there.
Sure. So this, what we're seeing right here, this is
Yep.
these dots right here on the side.
100%.
Okay.
That is correct. Yep.
Yep.
Absolutely.
So if this was in the middle of the block, we didn't know these dots were here. Now we're seeing what's happening there on the inside. Yep.
Yeah, you know, usually your parts aren't sectioned for you, so you can see
Sure.
the flaw inside the part.
Yep,
So
yep.
that's the idea, right? So you can see it pretty easily, very clearly, when you have really good material.
Yep.
And then we have flaws,
Okay.
reflections. Does that
Yeah.
make sense?
Yeah.
Yeah. And as you can imagine, it's kind of hard to depict, but there are a lot of sound bouncing off. When you bounce off a circle, it's not perfectly coming back at you, right? It's scattering. So that's why you have so much sound falling behind it.
Okay.
There's a bunch of reflections that are scattered around in there. But this instrument's really smart. It can figure out what's going on with your sound and show you in a nice, easy image.
And is this similar to what this is showing over here? This is obviously using water as some sort of a conduit to show something.
Correct.
Okay. Yep.
Yeah, so this is closer to what we would call conventional ultrasonics.
Okay.
Okay? Closer in a way. What we're doing is we have a paintbrush scanner.
Okay.
And they call it that because if you can see our screen here,
Painting
it
over
looks
there.
kind of like you're painting a picture, right?
Yep.
And all you're doing, it has encoders on this that can track the movement of the transducer on the pipe. So you should be able to paint in the whole view. And do you see those little yellow spots there?
Yep. Imperfections.
Yes,
Yep.
that is the wall thickness thinning.
Okay.
So I'm finding a low spot,
Yeah.
a low wall thickness spot, right? So what I'm looking for is corrosion usually in these pipes.
So this would this be considered mild corrosion and this is more serious?
Yes.
Yeah, yeah.
And you can set up your gradient in different ways, of course. You can set up different color schemes, but yeah, you can see the white in here would be a severe loss of
Okay.
wall thickness.
Yeah.
Where the yellow is just a mild version.
Yeah.
Does that make sense?
As much sense as I'm going to be able to understand it.
Of course.
Yeah.
The water on here, all it's doing is taking the place of that couplant, of
Okay.
that jelly. So like I said before, we don't like air in ultrasonics. So the water is a constant stream
Sure.
of a liquid
Yeah.
to eliminate the air.
Okay.
That's the only purpose of serving. But then of course you need a pump and you need everything else attached to it. But
Yeah.
it's super useful to be able to provide a data file that shows here's your pipe and here's all the corrosion you have on it.
Yeah. So the water is coming through this tube right here. So let's
Correct.
pretend you had to dig into the ground and you found this pipe.
Okay.
What piece comes with? This comes with, got
Sure.
a bucket for water,
Yep.
this.
You provide a water, you provide this.
Yep,
Usually
you
you don't
don't
have a
need the
monitor.
TV,
No,
right?
no,
Yeah,
usually
yep,
don't
yep.
have that. That's just
So
for
this is the
display.
piece you're bringing with
Correct.
some water. Yep.
Yep.
Okay.
This is a pretty simple purpose. What we're seeing here, this is called the C-scan.
Yeah.
Okay. This is what we call a plan view. It's a top-down view of what's happening here. So we're flattening down this pipe, and this is what we have, our flattened pipe. And you're looking straight down on that, so you can look in the spot. You can easily depict kind of the size of the corrosion
Yeah.
and the severity, right? So you would need the pump, you need the transducer, and you need your instrument.
Okay.
And of course the water source. And all you have to do is set up, you do your encoder calibrations,
Yeah.
you get your gradient in place, and then you can just start to scan, and you can see what's in your pipe.
And once you have this data, let's say we've identified there's this problem here.
Sure.
What do you do with it? Did you export it? Hey, Mickey, this pipe's right here. You cut it right here and fix it, or?
Sure, that really depends on what's happening, the
Sure.
contract, right?
Yep.
Sometimes we're just inspectors and we don't touch the repairs or we don't do anything else. Sometimes your company might have guys come with you that can do the repairs themselves,
Okay,
right?
yep.
Usually this gets sent to engineering.
Sure.
We always work with engineering because these wall thicknesses, these might look like a really big problem for us,
Yeah.
but I don't really know the purpose of this pipe usually.
Sure.
You know, I don't know exactly what it's doing.
Yeah.
So we send it out to get evaluated by the engineer.
They look at it in context.
100%.
Determine what to do now. Yep. All right, what are we doing here now?
Okay,
A little different scene than the computers
little bit.
over there.
a little bit dirtier too.
Yeah, awesome.
Okay. So this is magnetic particle testing.
Okay.
I've got Brody here.
Yep.
You go ahead and start, Brody.
Oh.
So he is doing a magnetic particle test.
Okay.
He uses magnetic fields to find cracks inside of ferromagnetic material. That's
Okay.
kind of important. It needs to be basic carbon steel.
Sure.
Okay. The magnetic field travels through the part, and what happens when you come across a crack, it has a few choices. It can go below it, can go all the way around, or it can just jump through it.
Yeah.
Jump through is usually easier for it. It always follows a path of least resistance.
Okay.
What's the interesting thing is that when you jump out and back in, you cause a north and south pole. That is your magnet, okay?
Yep.
So we combine that phenomenon that happens with these powder. They're iron filings that has a color attached to it,
Okay.
okay? Go ahead, shoot some on there. And what we find then is that where you have a crack, the powder
yeah.
gets attracted to it.
Right there. Yep.
Absolutely.
Okay.
So it's a very quick,
Yep.
easy, very efficient inspection.
All right. So what do we got going on here now? This is a little different.
This is a little different. We just talked about magnetic particle,
Yeah.
and I said that we can only do certain materials, right?
Yep.
This method is a little different.
Okay.
Okay. This is liquid penetrant testing.
Liquid penetrant.
Correct.
All right.
So we have a liquid that penetrates flaws. Does that make sense?
Yep. Yep.
Okay. What we do is we let it dwell for a while. We clean it off as best we can because we're never going to be able to reach inside that crack and clean it perfectly. Okay. Then we let it dry, and then we go through a development process. We apply a developer. In this case, it's a really fine white powder that tends to wick all the penetrant out of those cracks.
Okay. Yep.
So the end result here, you want to pick that up real quick, Mitchell? Give us a nice view of that.
Yeah.
We get a beautiful crack,
Sure. Yep.
and that is a penetrant. It's a fluorescent penetrant. It fluoresces under black light. Does that make sense?
yeah.
Yeah. It's a really easy inspection, but it's not that quick.
Okay.
Right? There's always a catch to all these methods, right?
Yeah. Yeah.
So in this case, when he puts it to dwell in the penetrant, he has to dwell for at least 10 minutes. Then he washes it off. He needs to dry for 5 minutes in the dryer. Then he needs to develop it, and then he needs to wait 10 minutes before he can do his final inspection.
Okay.
So it doesn't matter how big of a part you're doing, there's at least a minimum amount of time invested in each part.
Sure. Yep. Yep.
Yeah. So it's a pretty good job.
Is this able to be done in the field as well, or would this be something you'd take back to a lab?
Either or.
Either or,
We can
okay,
send it to
yep.
the field. We have a bunch of aerosol products
Yep.
that we can take with us, and then we can do the whole inspection out there.
Awesome.
If you're doing a fluorescent inspection, then you usually have to bring a black tarp with you.
Something like this.
Throw it over yourself.
yeah.
Yeah, you can do it. You can do all sorts of stuff out in the
Yeah.
field. But yes, 100% we can do that. This is one of the easy ones to take to the field.
Oh, awesome.
Yeah,
Oh, that looks cool.
absolutely.
All right, we're here with Mitchell. My name's Max.
Nice to meet you.
Great to meet you. Great to see you again. We were over there with the
Yeah.
liquid penetration test.
Yeah.
So you're currently in the NDT program. What is your favorite test you've learned so far?
Probably the liquid penetrant testing, just because it's more, you can actually you see it more in person than just on a screen.
Yeah.
So I feel like I don't know, to me it seems better that way. But ultrasonics, that's the only other one I've done. That one was really cool too.
Yeah.
Because it just, you see the discontinuities and everything, and then you map everything out. So
Yeah. Is this your first semester?
Yes.
Yeah, it's your first semester. What are you, I mean, it's maybe feels like a ways away. It'll probably come faster than you think. What are you hoping to do though in your career?
go X-ray welds on the pipeline, do radiography. It's kind of what I want to do, but I got a feeling I'm really enjoying ultrasonics, so I'm thinking something with ultrasonics at some point. So
Yeah.
we'll see.
Awesome. And based on your brief experience, how would you describe faculty, the program, just your experience so far in how this program's laid out, how they teach?
The whole program, it's kind of like a do-at-your-own pace. Like, I only come here 2 days a week just to do labs, and everything else I can get done at home. So I really enjoy that. Like, I live an hour away, so drive up here 2 days a week.
Yeah.
Staff here, extremely helpful.
Yeah.
Like, Sheldon, he's helped me out with so much. He helped me get registered and pick out all my classes and everything. And Walt, I just did liquid penetrant with him. He was extremely helpful throughout the whole process. So
Awesome. That's good to hear. Okay, so was NDT on your radar when you were in high school, or how close to graduation did you hear about this?
I was like 13 years old. We were down in Texas pig hunting. My brother was just like, you should consider NDT. I was 13. I was like, yeah, I didn't give much thought to it.
Yeah.
But then last October in Minnesota, it's free to apply to all colleges in Minnesota.
Yep.
So I was just like, okay, yeah, I'll apply for a couple different things to a couple different schools, wherever I get in, and then I'll decide from there.
Yeah.
And I ended up landing on this. I'm really happy I did, because I think it'll be a good career, and it's always going to be around too.
Yeah.
Versus like some other things are getting like outsourced or like done by, not needed anymore, or done by like computers now also.
Right. So if there was a high school student watching this right now, thinking that they're kind of interested, and what would you say to them, and what type of person do you feel like gravitates or does well in this field? You know, that there's a combination of a little bit of analytical mindset. They like data, but they also like to work with their hands. But what would you say to that?
To do this, to especially go through this program, since you can do a lot of it at home and you don't always have to be here, and none of them like nag you to do anything. You have to be very self-motivated and be able to hold yourself accountable. So that's a big thing. Then also, like, the same thing with work, you got to be accountable. Like, there's a guy in the town that I live in. He went through this program here, and he's been doing that ever since.
Sure.
And I think he's supposed to retire at 53. So which is pretty young to retire
Good age
now.
to retire, yeah.
And he's putting in like 70 hours a week, 40 hours out in the field, 30 hours at home doing all the paperwork.
Yeah.
So you got to be able, if you want to retire early, you definitely could in this field, but you got to be willing to put in the work.
Sure. Yep. And you have to enjoy the work.
Yeah.
If you're going to be putting in that much time.
Exactly.
Yep. Awesome. Well, thank you so much for
Yeah.
chatting with us. Appreciate it. Enjoy the program. Have a good rest of your semester. All right. So who am I sitting with?
Logan.
Great to meet you, Max Rath. Thanks for chatting with us. So we've been looking at the NDT program all day, seeing all the different tests, kind of getting some demonstrations. This is your first semester in the program?
Second.
Second semester in the program. Awesome. What tests have you learned so far, and what's kind of been your favorite ones?
I've learned everything from magnetic, particle testing, eddy current, both basic and advanced radiography, working on advanced ultrasonic. So far, my favorite has been advanced radiography.
Yeah. You're coming up on almost halfway through the program. So do you have your kind of vision set of the things you are probably most interested in pursuing in a career?
Still trying to figure some things out, but I would prefer more of a shop setting where things are brought to me.
Yeah.
We perform whatever we need to at the shop. If I had my way, I'd do computed tomography.
Awesome. And if there are prospective high school students that are watching this video, they think they're interested in learning the program or pursuing it, what do you think they would need to know to be successful in this program and in this career field? What kind of disciplines does it take?
Kind of disciplines? Just to show up to work, honestly, I guess. The work isn't too hard. It's really just about loving what you do, and what I love here is I have a sense of helping others despite not really directly doing so, protecting them from issues that may have occurred if I was not there.
Sure. Yep. Yeah. Well, that's a great point. That's a good way to put that. Yeah. And it seems like there's also a fair bit of just personal responsibility, and this program being a bit looser in terms of when you show up to do your work. You got to be willing to budget your time and be here for that. It's a balance of some analytical skills and also some desire to work with your hands, things like that. I mean, it's a lot of this is nothing to sneeze at. There's a lot of data and some technical work to it as well. So, awesome. Anything else you'd like to say to a high school student prospectively looking at this program and wondering if they're interested?
Just know that you will be called a hutch puppy from many prospective employers.
Which is a huge compliment.
Yeah.
Awesome. Thank you so much. This is the one.
This is the one. Okay,
All right, here we are.
this is an X-ray tube, okay?
Of course it is.
Produces X-rays when it's energized. It cannot be energized unless the door is closed. We're perfectly safe in here.
Okay.
There is no radiation output unless it is energized.
Okay.
Make sense?
Yep.
Just a source of radiation. The whole concept of radiography is that radiation is like a light, it's a ray, but it'll penetrate materials, right? So we use that to our advantage, where we put a part and we put film, photosensitive film below the part,
Okay.
and we shoot the radiation through the part into the film.
Sure.
That'll develop the film, and what you're looking at is the density differences in the material, right? As you can imagine, a cracked material
Yep.
is way less dense than the whole material, right where the crack is. And that's the differences that we're looking for. And what will happen is, once we develop your film, we go to darkroom where we can develop the film,
Okay.
okay? Now we have this nice automatic developer now. They'll just pop out your film. You put it on the other side, pops out.
Yeah.
The film is photosensitive, so radiation will develop it, but also white light will. So we have to load it inside of a cassette
Okay.
to protect it from white light.
Yep.
That's why we work in a dark room, so
Yep.
it doesn't get exposed.
Sure. And the end result is the same thing you'd get at like a doctor's office. That
100%.
Yep, yep.
I have a couple we can look at. If
Oh, awesome. Let's do it.
So this is our viewing room.
Here it is.
So we can use radiography for a whole bunch of things, right?
Yeah.
In this case, I have a nice valve here, right? They're trying to close this valve, and there is still liquid coming through. They're like, we can't get this thing closed. What's going on? What can you see here?
There's a wrench in the way.
Should that be there? Probably not, right? So this is one of the cool things that we can do with radiography, right? We're penetrating through entire components at a time. We're looking for those densities, and this wrench happens to be steel that is pretty dense, so we can easily see it contrasting with the area around it,
Yeah.
right? I have a couple others I can probably show you.
Yeah.
Let's look at these guys real quick. Let me see what's going on here. Okay, so this is a casting, and this is a little hard to see, but do you see all these little darker spots?
Yep. Yep.
This is what we call porosity in the material. Porosity is just gas bubbles.
Okay.
So casting, when you cast a material, you can have a lot of pores stuck in there.
Sure.
Does that make sense?
Yep.
And that's what we're capturing.
Yep.
I think we have other ones we can look at. This one's a little bit more interesting. All right, this one's a little hard to see. I'm gonna block part of this light here. Do you see this fine dark line right here?
Yeah, like a little crack or something.
100%.
Yep,
Look at
yep.
you. You're an NDT guy.
Well, I've been here all day now,
Yeah,
so yeah,
true.
it's starting to catch on.
So the darker it is, the less dense the material,
Okay.
right? So a crack shows up a nice dark line.
Yeah.
And when you have really dense areas where it's really thick, it shows up really white.
Okay.
Does that make sense?
Yep. Yep.
Yeah. So that's how we use radiation to our advantage.
Yeah.
And a lot of our technology that we use in NDT, we just straight steal it from the medical industry and say, we can use it for steel,
Yeah.
right?
Yeah.
And then we do that. And it works pretty good.
Incredible.
Radiography, what I showed you was an X-ray tube. What we also have is isotopes, so radioactive isotopes. And we have iridium and cobalt. I think just iridium and cobalt. I don't know. I'm not the RT guy. I'm not the RSO here, but that's what we can take to the field. Okay. Obviously, we can't take the X-ray tube in the field. That's mounted there. We've got a lot of safety devices in place for that.
Yeah.
We can take a source in the field and develop our shots, get a radiation wherever we need it to be. We use this interesting device called a camera. I can show you that
Yes,
real
I've
quick.
heard of those.
Yeah. This is a demo unit. It's pretty old.
Okay.
But this is how we store isotope. I told you radiation is like light, right?
Yep,
It travels
yep.
in a straight path.
Yeah.
What happens is when it's resting, it's in the center of this S-shaped part,
Sure.
right?
Okay.
This tube. So radiation can't get out of there. And this will be made out of lead or depleted uranium, something that's really dense and absorbs a lot of radiation. So no radiation comes outside of it.
Okay.
Does that make sense?
As
This
much
will
as it's going to make
protect it.
sense to me.
That's
Yes.
fair.
Yep.
It's a safe container that you can take it into the field.
Okay.
And then you have these crank devices, and you have a You have the in spot where you have a certain size, a lens, basically like a camera, like a collimator.
Yep.
And we can crank the source out to that end where we set up our shot, get our exposure, then we can crank it back into safety. So whenever it's out, it's upwinding radiation.
Sure.
So we always want to be pretty far away, maybe
Yeah.
create a barrier so we're not next to it.
Yeah.
We're really careful about managing our exposure to radiation.
Sure. Yep.
And generally speaking, we have a really safe practice, and it's, if you're getting radiation exposure, it's either intentional or you're taking shortcuts.
Sure. Yep.
Obviously, that's not something we want to do.
Right.
Interested in. Yeah.
Oh, fascinating. Very cool.
Yeah.
Awesome, Sheldon. Well, thank you for walking us through
course.
all that. This program's been around for quite a while, as I understand it.
Long time.
Yeah.
Way longer than I've been alive.
Me
okay?
too then. Yeah.
Yeah.
Yep. Yep.
So this started up as a co-op, and it was in the late 60s.
Okay.
And they were downtown Hutchinson,
Okay.
the building there.
Yeah.
And then they moved to this location, not this lab. This lab wasn't built that yet. They were, I think, further down this building. But it used to be called, let's see, it was Hutchinson Area Vocational Technical Institute.
Okay.
Okay.
Yep. Yep.
HOTV, or they called it VOTEC. All right. A lot of the guys, there's a lot of managers out in companies that come from VOTEC.
Yeah.
Guys that graduated in the 80s. This went from like the 70s to the 90s. Okay. And then after that, I believe it became the Hutchinson Community College, and then eventually became Ridgewater Community College.
Sure. Yep.
A little hazy on exactly the dates, but
Yeah.
I know we've been around since the late 60s, and that's pretty a long
Quite some time. Yeah.
Yeah, as I understand it, we're the longest running school for NDT.
Okay. Yep. That's what I had heard. Yep. So, I mean, in that amount of time, just industry partnerships, I imagine there's quite a few that we work with on a very regular basis.
100%.
Yeah.
Yeah. We tend to get a lot of old graduates, right? They're in the industry, they're leading the industry now. They will come back and they will connect with us. They always want to support us. So we have a lot of really good companies that sometimes they're desperate for help as well.
Yeah.
They will come to our students, they'll present to them, they'll hold interviews on the same day. Sometimes they're hiring people before they even graduate.
Sure.
Okay.
Yep. Yep.
They're desperate for people out there, so we're giving as much as we can.
Yeah. So there's a lot more demand than there is supply right now, especially in this field.
100%.
Yeah,
yes.
but let's talk about starting salary and just what people can do in their career. I mean, typically, where do people end up? If they're already coming out of college with a job,
Right.
great start, right?
Great start.
That's further than a lot of people. Where do we sort of see people start out, and then what does it look like as they begin to, sometimes you said like specialize in one thing and get their certification?
That's right.
Yeah.
Yeah, okay, so first thing I'll mention is that our placement is as high as you want it to be.
Sure.
The only reason you don't get a job is you don't want to go somewhere where the job is.
Sure.
Okay?
Yep.
We generally have more offers than we have graduates. All right.
Wow.
The problem is if you really want to stay local in Hutchinson, it's a
Yeah.
little harder for us. We
Sure.
go where the industry is.
Yeah.
Right?
Yep.
Where things are being manufactured, where the piping is, things like that. So
Yeah.
oftentimes our jobs will involve travel. Not always. You can be nested in the same company, or you might take a traveling job. Right locally here, the wages are not super high because we put out so many students that kind of want to stay local.
Yeah. Yep.
So usually when they get hired between I've seen as low as 22,
Yeah.
and I've seen close to 30, but usually talking like $25, $26 an hour.
Sure. Which
okay?
is nothing to sneeze at. I
No,
mean, that's a
that's
great
a decent,
starting salary.
It's a
Yeah.
decent pay.
Yep.
Especially when you take into account that is a trainee position,
Yeah.
right? They don't have any experience. They have all the training they need, they have no experience.
Sure.
If you're willing to relocate, that's where you can make a lot more money. They're being hired at $30 an hour.
Okay.
Okay.
Yeah.
And of course, it only goes up from there when you have your certifications.
Yeah.
You're looking at the $45 an hour.
Yep.
Some people are getting up to $50, $60 an hour, right? That's when you start reaching the six figures, and that's really nice.
Yeah, I suppose. I mean, that sounds like a very solid industry to enter into, especially if you come into it, 25 bucks an hour starting, phenomenal. Cost of the program typically. I mean, first of all, how long does the program take, and then what's typically the total cost for graduation, let's say?
Of course, yeah. So it's a 2-year program. We have 2 paths for 2 years. There's a diploma path, and there's a AES, Associate for Applied Science. And they're both 2 years, same amount of credits. However, the AES includes some general education classes, which our employers tend to prefer in the industry, right? It gives you a lot of those soft skills that they're looking for.
Yep.
Does that make sense?
Yeah.
The cost of the program lies somewhere between $12,000 and $15,000. That's not a semester, that's an entire program, right? The 2 years. You have book costs, you have your tuition, but we have a ton of scholarships. That's free money for them. So the cost will differ quite a bit from person to person.
Sure.
But you're looking at less than $15,000.
Sure. So 2-year investment, let's say $15,000, come out the other end, $25 an hour, quick and dirty math to a salary is about 50 grand. Sure. So a return on investment could be somewhere around that 45 to 55 grand, $15,000 education.
That's right.
That seems like a pretty sweet deal. Yeah.
Yeah. And then when you consider advancements in careers, right?
Yeah.
So I said you go from a trainee to a level 2. We also have another position called level 3. Those are the subject matter experts in the field. And those, you'll be hard pressed to find a position that is not a 6-figure position.
Oh, wow.
That's usually a salary position. So I think a lot of people that get into industry, into NDT, they want to work their hands. That's why they got into it. So a lot of them tend not to move on to the level 3 position because that's when you're writing the procedures, we're doing training, things like that. So a lot of people don't go that route, but it's available for the people who are, want to navigate that way.
Yeah, absolutely. So walk me through a little bit. It probably varies, on a week-to-week basis, but what does a typical week look like for someone at this? We're in the 3rd week of a fall semester right now. So what's a week-to-week kind of looked like for these new students?
Super hard question to answer, okay? The reason is that we have a pretty unique program here, and our schedule, we don't have scheduled lectures for our classes, okay? We're an open lab. This is what we call a hybrid or a flex lab style. What that means is that we have some online instruction. You can take your book home, read, you can take your tests at home, your quizzes, things like that. And then you come into the lab when you need to do your job sheets, is what we call them, but they're lab assignments, right? And what day you come in out of the week, that's up to your schedule. Okay. I'm not dictating that to you. You come in when you're available. As long as you get your weekly deadlines done for me, I'm not going to ask you to be here in a specific time. So this is really cool for our students because it allows them to work a job, right? They can work in the morning some days, and they can miss a few days a week if they need to. And if they work afternoons or night, they can come in every single day. Maybe they can get ahead in their classes then, right? So their typical day or typical week is really hard to predict. Sure. It's whatever their schedule dictates. We like this method because this is where we want to teach it before they get into the industry. Sure. Does that make sense? Yep. And it's really fun to see the difference between the first semester and the 4th semester in students, right? How much they have come along and how much they show up on Monday mornings, right? Because they have so much work to do, they show up and it's really cool. It's really inspiring to see. And that's why we're here, right? We want to put out these guys that are really solid in the industry.
Awesome. All right, final question. If I am a prospective student and I've watched this and I thought, NDT is the game for me.
Of course.
At Ridgewater, what do I do next?
You're a very logical person, I love it.
That's the first thing. You're a smart person, very logical.
Good choice,
What's my next step?
Okay. So the easy way is to go to our website, ridgewater.edu, and there you can find the request information, and you can put in what programs you're interested in. Make sure you include ours, obviously. We're the best program. And that's the next step. And then we'll send you a whole package of stuff, information, who to contact. If you have more questions, if you want to tour the lab, we love to show off our stuff.
Schedule a visit down there.
100%.
Swing by here, say hi.
Absolutely.
Yeah, that'd be excellent.
We always have our doors open. Community members, prospective students, anybody. And old graduates too. We love to get these people from the industry come in and checking out the old spot.
Awesome. Well, thank you so much for your time. Absolutely. Appreciate it. You heard it here. If you got any more questions, ridgewater.edu. Check out our NDT program. Meet some of our great faculty like Sheldon and all the others. We'll see you next time.